In this lesson, we're going to discuss the topic of curve sketching. And curve sketching is the process of putting together all of the analytics of a function in order to create an accurate graph. The different types of information we can derive from the function, its first derivative and its second derivative, we want to list out here and discuss, and that's how we will use as a frame of reference as we go through example problems. So the things that we can get from the original function itself. Domain and range can be helpful, although that's not always the most important thing to get when you're trying to find a graph. X and Y intercepts certainly are very important when trying to graph. It gives you a couple of points to plot and generally easy to come up with. Location of any vertical asymptotes or holes in the graph, and location of horizontal or oblique asymptotes, as the case may be. From the function's first derivative, the things that we can determine, as we've talked in the previous lessons, the location of critical numbers, which gives us the location of relative extrema, minimums or maximums that is, and intervals where the function is increasing or decreasing. From the second derivative, the things that we can determine, location of inflection points, which helps us find intervals of concavity. Because if we know where the function's increasing, decreasing, and where it's concave up and concave down, we have an idea of how that function is shaped. Because recall that we said there are really only 4 basic shapes to the graph itself. And as a reminder, the different shapes of the graph are, starting with a function that has a first derivative that's positive, which means it is increasing, or a graph that is first derivative is negative on an interval, so it's decreasing. If the second derivative is greater than 0, we know that that is concave up. And if the second derivative is less than 0, we know that that is concave down. Alright, so what those look like, I'll just put some extra lines in here. If you're increasing and concave up, then your curve looks something like this. So it's moving up in y value, but it also looks like it would be part of an upward facing parabola. Okay? If you are decreasing and concave up, then your curve would look like this. So the y values are getting smaller, but you're still looking like you're part of an upward facing parabola. If you are increasing and concave down, that looks like this. So the y values are getting larger as you go from left to right, but it looks like a downward facing parabola. And then decreasing and concave down would look like this right here. So if you know the values and the different intervals for where your first derivative and second derivative are positive and negative, you can determine what type of shape your graph has on those intervals, which can really lead you to a very easy way of determining what its graph should be. Let's take a look at an example. I've got a cubic function, negative x cubed plus 3x squared plus 9x minus 27. And what I would like to do is produce a graph of this, and I'll get started looking for the information that is useful from the the original function. So x and y intercepts, let's begin there. Alright, so y-intercepts, since this is a polynomial, the y-intercept is pretty easy. It's just where if you let your function be evaluated at 0, what happens here is all of the terms with an x go to 0, so you're just left with that constant. So negative 27. So the point 0, negative 27 exists on my graph. So I've got a point. I'm not going to plot it just yet, just because it is a very low value. I'm going to wait to choose a scale that's appropriate based off of other points on the graph. Let's look at x-intercepts. X-intercepts occur where the function itself is equal to 0. So you're letting the y variable be equal to 0 in solving. To do that here, we would need to set negative x cubed plus 3x squared plus 9x minus 27 equal to 0 and solve. And you might be thinking that since this is a cubic, it's going to be rather difficult to factor and come up with the solutions. And you might be right, but consider one factoring technique that often gets overlooked, and that is factor by grouping. In a cubic, you have 4 terms that you can work with. Factor by grouping only applies when you have 4 terms. So often in calculus and beyond, if you're given a cubic that needs to be factored, generally it will factor by grouping. It doesn't have to, but the problems we give you often will. So for instance, if I group together the first 2 terms, oops, that's still a negative, sorry. Where's my eraser? There it goes. Alright, so negative x cubed plus 3x squared. So I'm just grouping to the first 2 terms together, and I'm going to group the second 2 terms together. In the first 2, there is a common factor of negative x squared. And I'm pulling out the negative because if your leading term is negative, factoring is generally easier if you go ahead and pull that out as a common factor. So that leaves me, let's see, x minus 3 on the inside. And in the second group, I have a common factor of 9, which leaves me x minus 3. Now, if I look at what's left, I basically have 2 terms, and each of those terms has a factor of x minus 3. So I can pull that factor of x minus 3 out, and that's going to leave me negative x squared plus 9, or I'll write it as 9 minus x squared to make it a little bit more clear. Then the last thing here is 9 minus x squared is the difference of squares. So that would leave me x minus 3 times 3 minus x times 3 plus x. And if I look at the zeros of this, that's going to be the location of x-intercepts. So where x is positive 3 would make the first factor 0. Positive 3 would also make the second factor 0, so I don't need to list it again. And x equals negative 3 is another place where the I would have a 0. So I can go ahead and plot these. I think it's safe to do that. The scale on the x-axis I'll use as 1. And positive 3 and negative 3. Plot those in. Okay, so there are x-intercepts and y-intercepts. And let's go on to the first derivative, because since this is a polynomial, there aren't going to be any asymptotes, vertical or horizontal. That's really only going to apply if I have some type of division or rational function involved. Okay, so we'll scroll on down here and start working with the first derivative. Alright, the first derivative, I need to set it to 0, and I will have 0 equals negative 3x squared plus 6x plus 9. Now, there's a common factor of negative 3, and again, that leading term coefficient is negative, so I'm going to pull out a negative 3 instead of just 3. And that will leave me with x squared minus 2x minus 3, which is a little bit easier to factor. So negative 3 times, let's see here, x and x. If this is 3 and 1, it looks like it'll factor just fine. The 3 should be negative and the 1 should be positive. So that means I have critical numbers at x equals 3 and x equals negative 1. The negative 3 in the front is a constant multiplier. It doesn't lead to a 0. So negative 3, don't list that. It's just positive 3 and negative 1 from the individual factors that have a x in it. Now, I need to determine if my function is increasing or decreasing on these intervals. So I will put negative 1 and 3 on a number line, and within the intervals of those, find out where my function's increasing or decreasing. Alright, so picking a number inside each interval, I could use negative 2, 0, and 4. Now, on this interval from negative infinity to negative 1, I need to find out if my function is my derivative is positive or negative, telling me if my function is increasing or decreasing. So I'm going to plug it into that form of the derivative right there, because that's going to be the easiest computationally. So it's negative 3 times negative 2 minus 3 times negative 2 plus 1. And remember, all I care about is whether this is positive or negative. So it's effectively negative 3 times negative 5 times negative 1. And negative times a negative times a negative, that's going to result in a negative. So I'm decreasing on that interval. If I put in 0, it's going to be a negative times another negative, because 0 minus 3 is negative 3, times a positive. So negative times positive would result in a positive answer. And if I put in 4, it's negative times positive, which would result in a negative. So my function would be decreasing, come to this critical number, and then turn and increase. That means this critical number has to be a, sorry, not a maximum obviously, a minimum. So on the other critical number, I go from an interval that's increasing and then turns to decreasing. That's going to be a maximum. Great. We know what's happening with our first derivative. The only thing that might be nice is where the y values are for these. So, for instance, if I compute f of negative 1, I already know what f of 3 is, because if you'll recall, 3 was a 0, and if it's a 0, it's an x-intercept, which means the y value is 0. So I just need to evaluate the function at negative 1. Shouldn't be too bad. Let's see. It would be negative of negative 1 cubed plus 3 times negative 1 squared plus 9 times negative 1 minus 27. That would be negative 1 cubed is negative 1. Applying another negative, that's going to make it a positive 1. Negative 1 squared is positive 1. So plus 3 minus 9 minus 27. So f of negative 1. When we combine all this, it looks like negative 32. Okay. Now we're done with the first derivative, so let's move on to the second derivative and learn about concavity. So with concavity, we're looking for the second derivative, and we'll first come up with inflection points, which is where the second derivative is 0 or undefined. So the second derivative here, I'll call it y, since doesn't make a lot of difference, but I'll call it y just to be consistent. So the first derivative was negative 3x squared, so this is going to be negative 6x, and then it was plus 6x for the first derivative, so then plus 6, and then plus 9 for the first derivative, so that last term drops to 0. To get inflection points, I need to set this equal to 0 and solve. So negative 6 equals negative 6x, which means x is equal to 1. And we need to know the intervals for where this function is concave up and concave down. There's only one point where it changes. So on this interval from negative infinity to 1, we could test 0, and on the interval from 1 to infinity, we could test 2. We're just plugging into the second derivative here. So if I plug into the second derivative, negative 6 times 0 plus 6 is 6, which is a positive number. And then 2 will be negative 6 times 2, which is negative 12, plus 6, which is a negative number. And lastly, we'll probably want to know the y value associated with 1 so that I can get a decent graph. So I'm just going to plug 1 into my function. So f of 1 would be negative 1 cubed plus 3 times 1 squared plus 9 times 1 minus 27. And there's my equals. Geez, smart board. Thanks a lot. There we are. Equals negative 1 plus 3 plus 9 minus 27. And we add those all together, it looks like we get negative 16. All right, so I think we have all the different points that are useful here. So we can go back to our graph and see what we can do. All right, so the points of interest we had, I'm going to copy a few things back up here just so we can see them. So first derivative, second derivative. For the first derivative, the points of interest were at negative 3. Oh, no, that was the original function. For the first derivative, we had negative 1 and positive 3. And we learned negative 1 was a minimum. 3 is a maximum, because we were decreasing, then increasing, and then decreasing. Positive 1, and notice I'm trying to put these underneath where they would be on the scale of my graph. That was an inflection point, so I'm concave up over here and then concave down over here. The y values associated with each of these, so with negative 1 we had negative 32, and with 3 we had 0, and 1 we had negative 16. Alright, so we need a pretty large scale here. I've got 5 tick marks to work with. I've got to get down to negative 32, so I think an easy one would just scale everything by 10. Alright, so this first tick mark below the x-axis will be negative 10, negative 20, negative 30, and so forth. Alright, so I will plot these points. So negative 1 and negative 32. That would be about right there. And 3 zeros already plotted. 1 and negative 16. It's going to be approximately right there. I had a y-intercept that I found was negative 27, so 0 and negative 27. About right there. And let's see. So this value here was a minimum. So the graph's has to come through and make a minimum. This point was a maximum, so it's got to look like that locally. Alright, now to make this all fit together, let's think of this. If I am on this first interval, from negative infinity to negative 1. I'm decreasing in value, but I'm concave up. So the y values are decreasing, but I'm concave up. And, oh, all the way to negative 1. Okay, so I need to continue on. Decreasing, concave up, all the way to negative 1. All right, so that looks good. Then I'm still concave up, but I turn and I start increasing in values. So kind of looks like an upward facing parabola at that point. Then I go from, I stay increasing on the next interval, but then I become concave down. And I'm just reading this chart below me here. So decreasing and concave down looks like that. And then I am decreasing and concave down, which looks like that. So there is a pretty decent graph of my function. All right, ignore the little blue lines that I have at positive 3. Of course, that was just for emphasis there. But you can see how you can take the interpretation of the first and second derivative, whether it's positive or negative, and put those together and make the shape of the graph. All right, our next example, we have a rational function, y equals x squared plus 18 over x squared minus 9. And the thing that we need to pay attention to here is that there is a potential for asymptotes. You could have vertical asymptotes, horizontal asymptotes, and so forth. So we're going to spend a little bit more time with the original function than what we did with the previous example that was a polynomial. It's always best to express your rational in both factored and non-factored form. If you'll notice, x squared plus 18, that's not going to factor because it's x squared plus 18 and not x squared minus 18. But x squared minus 9 will factor. It will become x minus 3 times x plus 3. That's going to help us get the pieces that we need for asymptotes and such. All right, so beginning with x-intercepts. X-intercepts occur where the function itself is equal to 0, and in particular for a rational, it's just where the numerator is 0. But the thing is, this doesn't have any zeros because I move the 18 over and end up with x squared equals negative 18. So there's just no solutions, which means there's no x-intercepts. All right? Y-intercept is generally pretty straightforward, especially with a rational. It's where you let x equal 0. And so if you let x equal 0, then what happens is you get y, I'll be more specific here, y evaluated at 0 would be 18 over negative 9, which is negative 2. Okay. Horizontal asymptotes. You can have horizontal asymptotes. There are rules for this. Effectively, what you're doing is a limit as x goes to infinity. So if you don't remember those rules of horizontal asymptotes, remember this. It's a limit as x goes to infinity, in this case of x squared plus 18 over x squared minus 9. If you plug in infinity, your functions in the numerator and denominator go to infinity, so you can apply L'Hopital's rule. So by L'Hopital's rule, this is the limit as x goes to infinity of 2x over 2x. The x's cancel away, leaving you 2 over 2, which is 1. Also, if you recall those rules for rational functions, you're free to use them. However you do it, this is where your horizontal asymptote is, at y equals 1. Vertical asymptotes. Vertical asymptotes are going to occur where division by 0 happens. So that's going to be the zeros of the denominator So in this case, it would be at x equals 3 and x equals negative 3. So we already have a lot of information about our graph. Let's put things together, see what we can do with it. All right, now, vertical asymptotes we'll just fill in as dashed lines where those things are happening at negative 3 and positive 3. Horizontal asymptote, we had that at positive 1. And then we had no x-intercepts, but we did have a y-intercept at 0, negative 2. And I don't think we're going to have a lot of points here like the last example that go, much higher or lower than, positive 5 to negative 5. So I think we're free to just use the normal scale here. Now, what we need to do is determine what's happening within these bounds, where the graph actually exists. In order to do that, we need to know where the graph is increasing, decreasing, or where it is concave up or concave down. So we need to get first and second derivatives in order to determine that. All right, let's look at the first derivative. And unfortunately, because this is a rational function, in order to get the first derivative, I will have to use the quotient rule. So let's get started. With this, I will begin using the box here that I always do. X squared plus 18, and then x squared minus 9. The derivative of each one of these is 2x. And I need to multiply these two together first in my numerator. Now, I am going to need to simplify things when I get my derivative because, number one, I have to work analytically with my derivative, and number two, I do have to get a second derivative. So I'll go ahead and start simplifying. I'm going to take 2x, multiply it into x squared minus 9 to get 2x cubed minus 18x. Then I will subtract from that, let's see, 2x times x squared would be 2x cubed. 2x times 18 would be 36x. Great. Now, this negative distributes, and when that negative distributes, it makes this a negative and this term a negative. Okay? So, what's nice is positive 2x cubed and negative 2x cubed are going to cancel each other out and make things a little bit better looking in the numerator there. We still do have a denominator. We haven't finished out the quotient rule. We have to divide by the original denominator squared. Alright, so that means negative 18x, negative 36x exist in the numerator, which will combine to negative 54x. Then I have x squared minus 9 quantity squared. Okay, there's my first derivative. And my first derivative, when you set your first derivative to 0, the thing you have to recall is that you can change from increasing to decreasing when your first derivative is 0 or when it's undefined. So you need to get zeros of the numerator or denominator. So the critical numbers here, the numerator would be 0 if x is equal to 0. The denominator is going to be 0 if x is positive or negative 3. So going back up here, I'm going to put a number line in for my first derivative. Here's 0, negative 3, and positive 3. Notice that I still have the same locations as the asymptotes. Every single derivative is going to have something happening at those same asymptotes. So if you have a vertical asymptote in the original function, you're going to have it in all derivatives as well. Now, what we need to do is test on each interval, and you're fine to use your calculator to test on each interval. I don't have a problem with that. And if you want to get the y values of different functions as well, that's fine. But please don't use your graphing portion to get the graph. You need to show your analytics in order to get full credit for these problems. But if you do want to use the calculator to determine whether the first derivative is positive or negative, that's fine. Sometimes it's actually not too bad to use just the first derivative. It's like the denominator, for instance. Since it's x squared minus 9 quantity squared, no matter what you put in for x, you're going to square it, and you're going to subtract 9, but then you're going to square everything again. And when you square something, it's always going to be positive. So the denominator is always going to be positive. The numerator is an easy check. A negative number times whatever test value we're using. So on the first interval, we could use -4. So negative 54 times -4 is going to result in a positive answer. And between -3 and 0, we could choose -1. Negative 54 times -1. Negative times negative is a positive. On the next interval, we could use +1, so negative times positive is a negative. Then we could use +4, so negative times positive is negative. Alright, so now we know that our function is decreasing and increasing on certain intervals, but we need to know where it's concave up or concave down. So we still have more work to do. We need to get that second derivative and do some testing. Alright, so the second derivative, here you can use the quotient rule, or you can use bringing the denominator up into the numerator and then using a product rule. Doesn't really make a whole lot of difference. I'll just use the quotient rule. No particular reason. X squared minus 9 quantity squared. Alright, so the derivative of -54x is -54. The derivative of x squared minus 9 quantity squared is 2 times x squared minus 9 to the first times 2x. These two pieces are going to multiply together first, so my second derivative would look like -54 times x squared minus 9 quantity squared minus, and since it's at -54x, I'll just say plus 54x times 4x, just 2 times 2x is 4x, times x squared minus 9 all over x squared minus 9 quantity squared, which now makes this to the 4th power. Alright, so unfortunately, we do have to clean this up because we need to work with it analytically. But it's not going to be as bad as you think, because if you look here, there is a common factor of x squared minus 9 in every single one of these terms. That just cancels away. So this x squared minus 9 cancels one of these and cancels one of these. Now it cancels each of those because when you take a polynomial divided by a monomial, which is effectively what all instances of that term get canceled away. Alright, but that's nice because it cancels out more things. -54 I need to distribute, and we'll need to use a calculator for that, but let's see what happens here. Alright, so -54 times x squared is -54 x squared. -54 times 9, just grabbing my calculator here. LFIT will turn on for me. Alright, -54 times 9 is -486. So plus 486 because it's negative times negative. Alright, and then 54 times 4 that is, I think, 216. Yeah, 216. So plus 216x squared all over x squared minus 9 to the third. This is already looking much better. Negative 54 plus 216, that's going to be 162. So 162x squared plus 486 all over x squared minus 9 cubed. And wouldn't you know it, but 486 divided by 162 is 3. So I can actually factor out 162, and that's going to leave me 162 times x squared plus 3 all over x squared minus 9 cubed. Okay, so that gives me a function where I can come up with critical numbers. Or technically they're not critical numbers for the second derivative, although they're the same idea. They're potential inflection points. So let's see. The numerator would be 0. There we go. All right, so the numerator would be 0 where, well, nowhere, because x squared plus 3, if you set that to 0 and try to solve, you end up with complex numbers. So numerator can't be 0. The denominator still can be 0 at positive 3 and negative 3. So those are my potential inflection points. So I come up here, this time put my second derivative on this chart. Negative 3 and positive 3 are the points of interest again. Now I just need to know where this thing is increasing or, is concave up or concave down. So I'm going to choose some test values and put into my second derivative function down here. So I could use negative 4, for instance. So negative 4, the numerator, kind of interesting. It doesn't make any difference. If I put a positive or a negative number in for x squared, it's going to become positive. Then if I take a positive number and add 3 to it, it's still going to be positive. Then if I take whatever that is, which is positive, times another positive, the numerator is always going to be positive. So effectively, it's just the denominator that matters. So if I put in negative 4 to the denominator, that would be 16 minus 9, which is a positive number. When I cube it, it's still going to be positive. So that means this first interval is concave up. Then, between negative 3 and positive 3, I could use 0. So if I put in 0, 0 squared minus 9 would be negative 9. When I cube negative 9, I get a negative number. And then if I do positive 4, it would be 4 squared minus 9, which is 16 minus 9, which is positive. When I cube that, it's positive. So here's what I'm doing. In taking these changes, I'm effectively looking at this as a separate set of intervals where either the first derivative or the second derivative changes. So on this interval here, from negative infinity to negative 3, I am increasing and concave up. If I'm increasing and concave up, my curve has to look like this. On this next interval, where I change the first derivative is positive and then goes to negative at 0. So from negative 3 to 0, I'm increasing and concave down, which looks like that. Then I change from 0 to 3. I'm decreasing and concave down, which looks like that. And then lastly, I'm decreasing and concave up. So if I'm decreasing in value and concave up, it's going to look like this right here. So that's going off to infinity that way. Now, if we take that knowledge, I'll try and keep it on screen. I don't think I can. But we can take that knowledge and fit our graph where it needs to go. So in order to be increasing and concave up on this first interval, I have to bend toward my asymptotes. The only thing that makes sense is that as my graph portion. Alright, on the next interval, to be increasing but concave down, also have to go through this x-intercepts. I'm going to look like this. Then I change and I'm decreasing. So it's going to look like that. Then I'm decreasing but concave up. It has to look like this on that remaining interval. There's our graph. Alright, let's sketch a graph of the function y equals x minus 2 to the 2/3 power. Now the reason that I bring up this one is sometimes technology can actually be misleading for this type of a function. I've tested it on your calculators and your calculator seems to draw it just fine, but I've seen other types of technology not draw it so fine. And the reason is how you go about graphing with that 2/3 as your exponent. So in these kind of situations where you can have ambiguity, it's good to have some sort of method to prove what the graph is supposed to look like and then work back into what's happening with technology and why it might be misleading. This shouldn't be too bad of an example because the derivatives I don't think are going to be terrible to come up with. But let's go ahead and get started and see what we can do. So first things first, we'll get what we can from the original function. But generally, those sorts of things are x and y intercepts. So let's start there. So beginning with an x-intercept. X-intercepts occur where the function itself is equal to 0. So if I take x minus 2 to the 2/3 power and set that equal to 0 and try to solve it. It may look intimidating because of that 2/3 power. But here's the thing. You have rules of exponents which say that if you are taking something to the 2/3 power, you can cancel it out by raising it all together to the 3/2 power. And you may be wondering where I'm getting 3/2 from. But the point is, rules of exponents say when you have one exponent raised to another exponent, you simplify through multiplication. And 2/3 times 3/2 is 1, which leaves you just x minus 2. 0 to any power is just 0. That looks a little bit easier. Now we're at positive 2. So x equals positive 2 is an x-intercept. I'll go ahead and plot that now. Y-intercepts. Y-intercepts occur where the x value is 0. So you have to evaluate your function at 0. In this case, it would be 0 minus 2 to the 2/3 power, which is negative 2 to the 2/3, which may look intimidating, but it's not actually all that bad. When you raise something to the 2/3 power, what you're saying is to use the numerator as an exponent and the denominator as a root. So you would take negative 2 to the 2nd power, which would be 4, and then the root is 3, so you actually want the 4th root of 3. And you may not know that right offhand, but obviously you can use your calculator for that sort of thing. So the cube root, did I just say the 4th root of 3? Sorry, the cube root of 4 is what I want. In order to get that, what we do is press the math button, and that gives you a cube root function. So the cube root of 4, 1.587, and even if you didn't know that that was a cube root, you can still raise it to the 1/3 power, and the calculator does this in the same way. So 1.587, so about 1.6. You can't be too accurate here, but there we are. That's about 1.6. Okay, now I don't think we're going to run into any kind of asymptotes because there's no denominator here. So let's move on to the first derivative. So with the first derivative, I will use the chain rule to come up with that. And what I will do is bring the 2/3 down as a multiplier, x minus 2 on the inside, and then I subtract 1 from my exponent. So it's going to be 2/3 minus 1, which would be 2/3 minus 3/3, or negative 1/3. And negative exponent means to take that thing down into the denominator. So this is effectively 2 over 3 times the cube root of x minus 2. Okay, so this first derivative, it's going to have, it's telling me about where my graph is increasing and where it's decreasing. Now, there's a point where that changes, and that's what's important to us. In order to determine where that changes, we need to find out where the critical numbers are, so where the first derivative is 0 or undefined. So let's see. The first derivative, it's not going to be 0 anywhere, because if you set the numerator to 0, you're just setting 2 equal to 0, which doesn't give you any information. But if you look to where the first derivative is undefined, that's going to happen at 2. Because if you put 2 into your first derivative, you've got 2 minus 2 underneath that cube root, which is 0. The cube root of 0 is 0. So you have 0 in the denominator. So we're undefined at 2, which means 2 is a point of interest for us for this first derivative. It's a critical number. I need to find out if I am increasing or decreasing on each side of that. So let's see. If I put, say, 0 in, because 0 is clearly on the interval from negative infinity to 2. 2 over 3 times the cube root of 0 minus 2. Thing that you need to understand about the cube root is that it's perfectly okay to take a cube root of a negative number. It's only a cube root of a square root of a negative number, or any even roots of negative numbers that we're worried about. So the cube root of negative 2 is defined. It's a negative number, and that's all we really care about. So everything on this interval is going to be negative, so decreasing. And if you aren't sure of my argument, use your calculator to prove it. So 2 over 3 times the cube root of negative 2. It's a negative number. It's irrational. It doesn't much matter what the actual value is. It's just that it's negative. All right, let's try putting in 3. So if I put the value 3 in, 3 minus 2 in that denominator would be 1. Cube root of 1 is 1. So it looks like it would evaluate to 2/3, which is positive, and that's all that really matters. So at this point right here, I go from decreasing to increasing, so this looks like it's going to be a minimum. All right. But one thing to pay attention to is that this isn't a normal minimum. It is a minimum where your first derivative is undefined. So it's not going to have this like smooth shape to it. It's going to be a sharp corner, right? So I think we discussed about how the first derivative is undefined when you have a sharp corner in your curve. So that's what's going to happen here. It's not going to be a smooth curve. It's going to have a sharp corner. All right, let's look to the second derivative now. So the second derivative still shouldn't be that difficult to get. With the second derivative, I will use the form of the first derivative, 2/3 x minus 2 to the negative 1/3, just so I can use the power rule. So this would be 2/3 times negative 1/3 times x minus 2 to the negative 1/3 minus 1, which would be negative 4/3, and then times the derivative of the inside part, which is finishing out the chain rule, but that's just 1. So that's okay in this case. So this becomes, let's see, negative 2 over 9 times the cube root of x minus 2 to the 4th power. Okay. All right. Now we have to get where this thing has points of interest, and that's going to be where the with this second derivative is 0 or undefined. Again, the numerator doesn't have any x's, so there's not any potential places where the numerator is going to be 0. It's only where the denominator would be 0, and that's going to lead to the second derivative being undefined. So it's undefined again at 2. And the reason is, if I take 2 minus 2, that would be 0. 0 to the 4th is 0. The cube root of 0 is 0, so you end up with this 0 in the denominator. So that's a point of interest for the second derivative as well. All right, around 2, we need to know if we're concave up or concave down. So let's see what happens. Now, if I am concave up or concave down, I could use, say, 0 into the second derivative, because 0 is on the interval from negative infinity to 2. So the second derivative evaluated at 0, 0 minus 2 in that denominator would give me negative 2. When I raise that to the 4th power, that's going to be a positive number. I take the cube root of a positive, it's positive, times 9, it's positive, but it's negative 2 divided by that positive, so this is concave down. And then if I put in, say, 3, 3 minus 2 is 1, 1 to the 4th is positive, the cube root of 1 is still positive, but I still have a negative up in the numerator. So negative divided by positive is negative. All right, and this actually is where this sharp corner comes from, because watch what happens here. So, well, let me do what I did in the last example. So I have here 2 is my only real point of interest. I'm on an interval that's decreasing and concave down, which is going to be shaped like this. Then I'm on an interval that's increasing, but still concave down, which is going to look like this. So at this point 2, there's going to be this sharp corner, because in order to change concavity that quickly, I don't have, something like this, all right? I would have to have another inflection point, an interval of concave up, but I don't have that interval of concave up. So these two things are joined together with this sharp corner. So that's where this sharp corner actually comes from, that sudden change in concavity. So that is a 0 of the function. I'm decreasing and concave down to this point. Then I turn and I'm increasing and concave up over here on this interval. So my graph is going to look something like this right here. And if you try this on the calculator, you should be able to verify. So let's just take a quick look and see what happens. If I put x minus 2 raised to the 2/3 power and graph graph. And there's the other part, just like we expected. All right,